Hey, today we're going to be talking about nonlinear factors of polynomials. This is also known as the complex conjugate theorem. That just sounds really fancy. So earlier in the week, you watched a video on linear factors of polynomials and how we can find the roots if we're given the factored form of a polynomial, and how if we're given the roots of a polynomial, we can write the linear factors and then use that to write the equation. So for example, what I'm talking about was when we had the factored form of a polynomial, then we knew that the roots had to be 4, -1, and 7/2, because we would take each one of these and set them equal to 0. So x minus 4 was equal to 0, so x had to be equal to 4. And x plus 1 was equal to 0, so x had to be equal to -1. And we get the fractions when there's that number in front of the x. So if 2x minus 7 was equal to 0, when you add the 7 to both sides, 2x equals 7, and when you divide it by 2, x was equal to the 7/2. So we had talked about that earlier in the week. And then we also did kind of the converse of that, the backwards of that. If you're given the roots, how do you then make it a list of linear factors? So we said that we would just kind of undo this step right here. So if we know -2/3 is one of the roots, that meant that x was equal to -2/3. So we kind of think of these steps backwards. So here I had divided by that 2, so that means to undo that, I need to multiply by that denominator. So that gives me 3x is equal to -2, and then if I just add the 2 back over to the other side, I get 3x plus 2 is equal to 0. So that's where that factor came from. When it was a single number like this, like an integer, that was a little easier. 18 was x minus 18, and -5 was x plus 5. But then we had a list of all the linear factors of that polynomial. So if we knew all the factors, you could find all the roots. And if you knew all the roots, you could write all of the factors. So that meant we could build all of these polynomials by its roots, or we could use a polynomial to find its roots or its solutions. Well, now I want to look at a situation that if you even go back a few more videos, looking at another polynomial in its factored form. So this was a perfect cube minus a perfect cube. And if you remember the factoring video, it had us do the sum and difference of perfect cubes. So if you remember, the pattern for factoring a perfect cube minus a perfect cube is to take the cube root of the first one. So the cube root of x cubed is x, and the cube root of the second one. So 27, the cube root is 3, because 3 cubed equals 27. And then we said to get the second factor, we took this first cube root and we squared it. We took the second cube root and we squared it. Then we took the 2 cube roots and multiplied them times each other. And then we used SOAP. Remember, SOAP stands for same sign, opposite sign, always positive. So this one was originally negative, so this was minus. This has to be the opposite, so it'll be plus. And then this one is always plus. So this is the factored form of that polynomial. Well, we also know this is to the third power. So I'm supposed to have 3 roots, because we did learn fundamental theorem of algebra back in Math 2, I believe, that said whatever the exponent was, when we did quadratics, we learned it had a square, so it has to have 2 answers no matter what. And it's the same for all polynomials. That's something we'll want to remember as we go through this unit. Quadratics are polynomials. So those rules that applied to quadratics generally do apply to all of the polynomials. They just have bigger exponents. But a quadratic is a polynomial. So it is to the third power. It has to have 3 roots. So here, if I do x minus 3 equals 0, I get that one of the roots is 3. But this one's still a quadratic. And if I try to factor it, 2 numbers that multiply to equal 9 and add to equal 3, there aren't 2 numbers that do that. In fact, this one does not factor. So I can't write this polynomial as a pure list of linear factors. In fact, it has one linear factor. This is a linear factor. Notice x is just to the first power, but this is a quadratic power or a quadratic factor. And when we do get a quadratic factor that doesn't factor anymore, I mean, you always want to check, see if it factors. But if you get a quadratic factor that doesn't factor anymore, that means that we have some roots that are not rational. They can't be written as a fraction. They can't be written as an integer. They're not rational. And we also learned when we studied quadratics that we also have things called imaginary roots. Remember, that's when we ended up with the square root of negative something, when we got that I. We also have irrational roots. Sometimes we didn't get a negative underneath the square root, but we would get a number that didn't have a perfect square root. It was left irrational. And so when we get this quadratic factor that doesn't factor anymore, that leads me to believe that I've probably got some imaginary or irrational roots. That's when we have to also go back and think about our quadratics. If I'm going to figure out what those two roots are, when we had a quadratic that we couldn't factor, our options for solving it were either complete the square, get it in vertex form, or to do the quadratic formula. All of those are legitimate options. If we were to do the quadratic formula on this one, we would do the opposite of b. So that's going to be -3 instead of +3, plus or minus the square root of b squared minus 4ac. So b squared minus 4ac would actually end up being -27, and then all over 2a, which would just be 2. So I've got a square root of a negative. That means, I do have imaginary roots. So now I figure out that I have, this I think will reduce because that's -9 times 3, and I can take the square root of -9. So I get -3 plus or minus, the square root of -9 was 3i, and then the square root of 3 just gets left underneath, and then it's all over 2. And then just like with quadratics, don't forget this isn't one root. It has plus or minus. That plus or minus means it's actually two separate roots. It's -3 plus 3i on the square root of 3 over 2. And it's -3 minus 3i on the square root of 3 over 2. So I did end up with 3 roots for this polynomial by factoring it. I did find all 3 roots by factoring it. It's just that this one factor didn't turn out to be linear. It turned out to be quadratic. And I had 2 imaginary roots. So that's one thing that I want to point out. Quadratic factors always give us 2 roots because they're squared. So they always give us 2 roots. So what do we even call that? So if we take a look, our next rule tells us complex or imaginary roots have to come in pairs. You cannot ever have 3i as a root of a polynomial unless -3i is as well, because the only way we would have gotten an I answer is if we had taken the square root of a negative number. But we also learned with quadratics that when we take the square root as a tool to solve something, it always, love that always word, always has to have the plus or minus. It's always going to be 2. So if we took a square root of something anywhere in the process of solving anything, then we always have to get 2 answers for that. We always get the positive version and the negative version. So any root that has I in it means you took the square root of something. And if you took the square root of something, it had to come out with a positive and negative version of it. Now, we do have a name for that. And so this pair of roots that come together are called conjugate pairs. Conjugate pairs. A conjugate means that it's got that plus or minus in front of it. So a lot of times you will see people write it as 1, just like we did when we were solving by quadratic formula. You would leave your answer as the plus minus. But conjugate pairs come from plus minus. So it's important to remember, if you have any root that has I in it, it is a pair. It is always a pair. So it always has a match. So let's look at a couple of examples. If 5i is a root, then that means that negative 5i also has to be a root. If you happen to have negative 3i as a root, then that automatically means that positive 3i has to be a root. They come in pairs. So there's that plus minus, the positive negative version. Now we also remember that sometimes these imaginary roots were complex numbers. Remember, they had a real part and an imaginary part. They still have to have conjugates as well, because they would have had a plus or minus in them. So for example, if I had 3 plus 2i as a root. So this is where we want to be careful. Remember where the plus or minus would go. It's not saying that you're going to change the sign and everything. You have to ask yourself, where's the plus minus? The plus minus is always in front of the imaginary number. So if this is the plus in front of the imaginary number, then its conjugate has to have the minus in front of the imaginary number. The real part didn't change. Just we were taking into account the plus minus in front of the imaginary part. If I have negative 7 minus I, again, remind yourself, where's the plus minus? The plus minus is in front of the imaginary part. So that means that the next one, its conjugate, would be negative 7 plus I. And so there's the plus minus. The negative 7 was still negative 7. The plus minus went over here. So how do we use that to help us find actual equations if we're given complex imaginary roots? So let's put this back together with what you did yesterday with the linear factors and the rational roots. We were looking at rational roots yesterday. How do we put that together and still write an equation if we're given the imaginary roots? So our first example is going to give us that we want to write the polynomial that happens to have roots of negative 5i, or negative 5, excuse me, and negative 3i. So let's just start with what that even means. One of the first things that pops into my head is it only gave me 2 roots, so I would think that's just going to be a quadratic, but then I noticed that this one has I in it. Some kind of bell or whistle needs to go off in your head and say, well, if negative 3i is a root, it had to be plus or minus. So that means positive 3i also has to be a root. They didn't tell us that. That wasn't given to us, but we know it for a fact because you cannot have an imaginary root without it having a conjugate pair. It has to be the 2 of them. Now, the good news is how we find the factor that goes with it is basically exactly the same as it was with linear factors. If you remember, if negative 5 is a root, that means that x equals negative 5. So to figure out what its linear factor had been originally, I would add 5 to both sides, and I get x plus 5 is equal to 0. So that means its linear factor was x plus 5. Now, if I want to do that with the imaginary root, so that means x must have been equal to 3i. Now, here's the cool thing with the imaginary roots. You don't have to do it for both of them. You can pick one of the 2 conjugates and use it, because when you put it back in its form, it's going to give you not a linear root or a linear factor. It's going to give you a quadratic factor. So it's going to automatically take into account both of them. They're a pair. They come together. You can't have one without the other. So I just have to pick one. I will say, for my sanity, I tend to pick the positive one, just because then I'm not losing negatives somewhere and making a careless mistake. You don't have to. You can use the negative one. I'm just saying negatives tend to be a problem. So if I don't have to use the negative, I don't. But as I'm looking at this, I can't do anything with the I. The I is the problem. So in order to get rid of the I actually need to square both sides of the equation. Because think back to Math 2. We learned that I squared, if you take the square root of -1, because that's what I is, and you square it, we learned that the square and the square root cancel, and it's actually just equal to -1. That was what we learned. I squared is equal to -1. It's not actually got an I in it anymore. And if this is an equation, as long as I do the same thing to both sides, then I'm totally okay. So then I get that x squared is equal to, now 3i times 3i is going to be 9i squared. But then we just talked about that I squared is actually equal to -1. So this is -1 times 9. So that means x squared is equal to -9. Well, now I'm almost equal to 0. In fact, if I just add 9 to both sides, I get that my quadratic factor is x squared plus 9. And then I notice I have x to the first and x to the second. This is going to give me an x cubed. In fact, to get the equation, all I now need to do is to double distribute, multiply. You can use the area model, the box method, whatever way you want to multiply these two binomials. If I double distribute, I'm going to get x cubed. And then, let's see, x times 9 gives me 9x. And then 5 times x squared gives me 5x squared. And then 5 times 9 is 45. So this would be the cubic equation. Notice it's to the third power, and we had 3 roots. So this equation comes from these 3 roots. So when you have those i's, you're expecting to get a quadratic factor, not just a linear factor. When you have a rational root, you're expecting to get a linear factor. Let's look at one more example. So how do you write an equation if you're given complex imaginary roots? And what if our roots are 1/2 and 5 minus I? Okay, so this time I have a fraction, but that's rational. That's a rational number, so I'm expecting that to be a linear factor. The second root, though, has I in it. And if it's got I in it, I'm expecting it to be imaginary. It's got to have a quadratic root. It also means that this should have been plus or minus. So it's 5 plus or minus I. So if I'm going to write this as a linear factor, if x equals 1/2, don't forget when it's a fraction, we want to multiply by the denominator first to get rid of the fraction. So we get 2x is equal to 1. And then if we just subtract the 1 from both sides, we get 2x minus 1 equals 0. And that gives us our first factor, our linear factor. So we know we have a linear factor of 2x minus 1. So now I have x is equal to, and again, I can use 5 plus I or 5 minus I, either one. They're both roots. I'm going to stick to the positive one just to make myself feel a little safer. If I have 5 plus I as my root, we said last time squaring it, but I don't have I by itself. I do want to point out that in order to square I and have it become just I squared and not have like a binomial that you have to expand out and still have an I stuck in it, you have to make sure the I is isolated first. So I do want to subtract the 5 first. In the last problem, it was 3i. That was a monomial. This is a binomial. So you can have a number multiplied in front of it because that will just make it 3i times 3i like we had in the last problem. But if I were to square 5 plus I, that's a binomial. I would have to double distribute or use the area model and get a trinomial, and then I'd still got an I. So we want to make sure that it's just a monomial with I in it. So that means if I subtract 5 from both sides, I get x minus 5 is equal to I. Well, now I want to square both sides, because if I square this side, I'm just going to get I squared. And we talked about I squared is just -1. But this is a binomial, and I do want to point out, you can't distribute an exponent. This has to be x minus 5 times x minus 5. So you can kind of go off to the side. If you do the area model, do a box, that's fine. X times x is x squared. I've got -5x and -5x, so that's going to be -10x. And -5 times -5 is +25. So that means I have x squared minus 10x plus 25 is equal to -1. Well, it's almost equal to 0 now. All I have to do is add the 1 to both sides. I said, I wrote 0. I meant to say 1. So if I add 1 to both sides, I get that this quadratic factor is actually x squared minus 10x plus 26. And so these would be my linear and my quadratic factor for those roots.